Have you ever wondered how neurons communicate? Underneath the seemingly simple process lies a complex and fascinating system of electrical charges and ion channels. Today we're going to delve into this intricate universe of neurons, starting with the concept of the resting membrane potential. Picture this. You have a car battery. It's not doing anything, just sitting there, but it's storing energy. Connect wires to the positive and negative poles and you can use that stored energy. In a similar way, there's an electrical charge difference between the inside and outside of a neuron when it's not generating action potentials, which we call the resting membrane potential. It's like the neuron's own battery, ready to power its communication with other neurons. And just like a car battery, we measure this charge difference in volts. For a neuron at rest, this charge difference is around minus 70 millivolts. Now let's add another layer to this: conductivity. You see, neurons have these things called ion channels. They're like gates made of proteins that control the flow of ions. When a lot of these channels are open, we say the conductivity is high. So if there are a lot of sodium channels open, sodium ions can flow easily into the neuron. But what happens when the ion in question is potassium, with a concentration 20 times higher inside the neuron than outside? Well, when potassium channels open, potassium ions start to move from the inside of the neuron to the outside, following their concentration gradient. But as they leave, the inside of the neuron becomes more negative compared to the outside. This creates an electrostatic pressure that pulls potassium ions back in. It's like the old saying, opposites attract, but happening right inside the neuron. To recap, the resting membrane potential is the electrical charge difference inside and outside a neuron when it's at rest, similar to a car battery storing energy. Conductivity in neurons is controlled by ion channels, and when many are open, ions can flow freely. And finally, the equilibrium potential of potassium is a balance between the concentration gradient that pushes potassium out of the neuron and the electrostatic pressure that draws it back in. It's a delicate balance, but it's key to how neurons communicate. So, next time you think about your brain, remember the complex dance of charges and ions that makes it all possible.